So hello everyone. This is Lance Lian from Penn State. So today I'm going to show you the function which is called the arrow function. So before we jump into arrow function, let me show you an exponential function. Okay, so let's assume the x-axis is x, and then the y-axis is exponential function e to the power of next x squared. Okay, so here is a plot for the exponential function. As you can see, the maximum value for this exponential function is 1, okay, which is when x equal to 0, okay? And then you can see there is a symmetry between x larger than 0 versus the x smaller than 0, right? There's a symmetry there. So basically, when you understand the function for x larger than 0, so you know the property for x smaller than 0 because there's a symmetry here, okay? So once we understand this exponential function, now I'm going to introduce to you what is the arrow function, okay? So first of all, the arrow function is defined as, so arrow function we write as ERF. So let's say arrow function ERF, let's say eta, is equal to 2 over square root pi, and then you integrate from 0 to eta, and e to the power of x squared dx, okay? So you can see here, it's an integration of this exponential function, okay? And then there are two questions here. First of all, the question is where this number come from before the arrow function, okay? The second question is why this function is called an arrow function, right? Where the word arrow come from, okay? So this arrow function is called arrow function. It's because of its historical origins in the study of errors in measurements in statistics, okay? So the term error in this context refers to the derivation or difference between observed values and true values, okay? So that's why it's called an arrow function, okay? This is where the word arrow comes from, okay? So the second question is where this 2 over square root of pi come from, okay? So actually this is coming from the integration of this function from negative infinity to positive infinity, okay? So when we learn statistics, we know that when you do the integration of a function, you are basically calculating the areas underlying this curve, right? Underlying this curve, e to the power of negative x squared, okay? But then the question is, what this number equal to, okay? What this number equal to when you do the integration from negative infinity to positive infinity, okay? What this equal to. So it turns out when you try to solve this problem, it's actually challenging to solve this problem directly, okay? So we have to do a transformation first. So we know this must equal to a number, a number such as 10 or something. It must equal to a number. But exactly which number this equal to, we don't know, right? So we can assume, this number is I, okay? Let's just say equal to a number, I. I is a number, okay? So then what we did is we can do, so we can do here, we can do another I times I, okay? Basically got I squared, right? So what you can do here is you can do integrate. You can do two integrations, and then you can have x squared plus y squared, and then you can do dx dy. Okay, so basically you have two I times each other, and then you got this integration function. So you may wonder, I even don't know how to do this simple one. So how can I do this more complicated one? So it turns out the math for the more complicated one can be done and is easy. Okay, so basically what you do is, so now you have the rectangular coordinate, right? You have x, y, z, right? So you want to do the transformation into the the radius coordinate, right? So you assume that r squared is equal to x squared plus y squared. Okay, so basically you got I times I, right? You got I squared that is equal to integrate from 0 to pi and integrate from 0 to infinity, and then you got e to the power of r dr d theta. Okay, and then based on this, you can easily solve that I squared actually is equal to pi. Okay, and then you got r equal to square root pi. Okay, so basically this guy is square root pi. Okay, so you are integrated from negative infinity to positive infinity. What if you are only integrate half of it? Okay, if you are only integrate half of it, basically from 0 to infinity, what you got is half of this number. Okay, so now you understand where this number come from, because they just want to make sure if your eta is infinity, then this thing become 2 over square root pi. And then what you got is this thing become 1. Okay, so basically, this is a normalization factor to make sure that ERF eta is smaller than 1. Okay, smaller than 1. So this is the error function. Okay, this is the error function. Based on this, we have a few features that we can know. So first of all, we know that the ERF eta is smaller than 1, right? Then that means we can define another function called ERFC, complementary error function, and we define that ERFC plus ERF eta, let's say they add up together equal to 1, okay? Add up together equal to 1. So based on this, if we write down the the definition, so what we will have is let's say ERFC eta is plus the ER, right? So that's 2 over square root pi, and then this is integrated from 0 to eta, and e negative x squared dx, right? And then equal to 1. 1 we can write as, what we can write? We can write as 2 over square root of pi and integrate from 0 to infinity, right? 0 to infinity, and then e to the power of negative x dx, right? We can write this, right? So now we can see, okay, so let me write down one more time. So basically you got ERFC eta plus 2 over square root of pi integrate from 0 to eta, and then e to the power of x dx, right? And this is equal to 2 over square root of pi. This is 0 to infinity, e to the dx, right? So basically, what is this? So you can move, what you can do is you can move this thing to here, right? So minus this thing, okay? So basically you are doing something 0 to infinity minus something 0 to eta. What do you got? You got eta to infinity, right? So if you don't understand this, you move this back, you will see immediately. So 0 to infinity is equal to something 0 to eta plus something eta to infinity, right? Did you see that? So you see, this part, and this is from 0 to infinity, okay? So basically this tells you that the ERF eta should equal to this, right? So 2 over square root pi integrate from eta to infinity, right? And then e to the power of negative x dx. Okay, so this is also what the homework problem want us to demonstrate. Okay, so I hope this helps. And the error function is very, very useful, not only in statistics. For example, in statistics, if we have, let's say we draw a curve like this, okay? Let's say this is the average heights of people in a city, let's say in State College. So for example, the average height is 5 feet, 5 feet, let's say 6 inches. And then this is talking about, and then someone, of course, will be higher, right? So you got someone that is 6 feet, okay? Someone may be shorter. Let's say someone is like 5 feet. So basically, what error function can tell you is the probability of people that is around 5 feet 6 inches. So for example, between one standard deviation. So if you calculate the possibility here, then that's the probability that people, that is around 5 feet 6 inches. Okay, and also the error function is very, very useful in mass transport. Okay, mass transport. So we know the concentration of any component, minus the concentration at the very beginning divided by the C1 minus C0. So this concentration actually relates to the 1 minus the error function of the position over square root 4 dt time. Okay, so you can see as long as you give the system your position and time, you can calculate exactly what your concentration is. So you can see here, error function plays critical role for mass transport problems. So that's why overall, the error function is a very, very important function in math, statistics, and engineering. Okay. So if you find this video helpful, please click like and also subscribe to my channel. Okay, thank you. Bye-bye.